We are now continuing with section 13.6, the normal distribution. We mentioned the normal distribution in the last recognition of distribution exercises, but we haven't actually covered it, so now we will do that. The most important, the most common, for certain, distribution is the normal distribution. It kind of has this shape. If you do it in bars, you can also do it with a curve and make a bell-shaped curve. It's called a bell-shaped curve. The graph of a normal distribution is called the normal curve. The normal curve is bell-shaped and symmetric about the mean. Symmetric about the mean means that if you sliced it right down the center, and I have a straight edge right here, sliced it right down the center, imagine that's perfect. Okay, I didn't quite get it straight. And folded the right side and the left side would make a mirror image of it themselves. It would land over here, over there. It's exactly symmetric. The right and the left side are the same around that line. It's symmetric about the mean. So this line that comes down the center, imagine it right down the center, is at the mean. The average is right in the middle. In a normal distribution, this is important, the mean, the median, and the mode are all have the same value, and they occur at the center of the distribution, physically in the center. Remember when we had skewed right or skewed left distributions, that was not the case. They were not the same number, and they landed in different places within the distribution. Okay, in a normal distribution, oh, we did that. Empirical rule. On all normal distributions, approximately 68% of all the data lie within one standard deviation of the mean in both directions. So from the mean, if you go up one standard deviation and down one standard deviation, you'll get 68% of the data. And then you'll get 95% within 2 standard deviations and 99.7% within 3. Now I've included a graph here to show you that is not one that was in your lecture printout handout, so don't think you missed it. I'm adding this in. On the graph, this is where the mean goes, right here. Okay? This is if you go up one standard deviation. So this is the cutoff with x plus whatever the standard deviation is. Remember, that's the average of the deviations from the mean. We did that in the section on measures of dispersion. Over here, this cutoff line is the mean minus one standard deviation. And they said that 68% of the data will lie within this region. So that means 34% will be in this part and 34% in this part. So if you pick some measurement, say height, suppose the average height in our classroom was 5'7", and the standard deviation was 1 inch, just to make it simple. It's more than that. Then this would be 5'7", that would be 5'8". You go up by the one standard deviation. 5'7" minus the standard deviation would give us 5'6". And if we had actually calculated those instead of me making them up, we would find that 68% of the population would be within that height range between 5'6" and 5'8", one deviation above and below the average. You'll find this true when you calculate all kinds of statistics, intelligence, shoe size, height of fully grown pin oak trees, number of leaves on willow trees, okay? This occurs all the time in nature, so that's the reason they say it's the most important distribution. If you go 2 deviations above the mean, in other words, if you start from the mean and you add 2 standard deviations to get to that cutoff point right here, and you do the same thing over here, this cutoff point will be the mean minus 2 standard deviations. And I've been using this symbol like that. That's the population standard deviation. And we earlier used S for the sample standard deviation. It's fine, okay? Just know that that's what the symbol. These are both symbols for standard deviation. Okay, so in this region we have 95%. So if you take 95% and you subtract this part in the middle and divide it by 2, you'll find out that this section here includes 13.5% of the population, as does this section right here, 13.5% of the population. All right, now we go to the cutoff at 3 standard deviations. So this cutoff is the mean plus 3 standard deviations. That's the cutoff here. Notice that the tail is still going out. It would still go out indefinitely. It would get so low that it's practically 0, but it would not actually touch 0. It's what we call an asymptote. It gets closer, but it never touches. Okay, so this cutoff over here is at the mean minus 3 standard deviations. And again, we take 99.7 and subtract the 95 we've already used, divide that equally on these 2 little sections, and we'll find that this yellow region right here contains 2.35% of the population, and this region over here contains 2.35% of the population. Okay. Now if you add that up, that's not 100%. And to be complete, we have to have the entire graph, which means that out here in these little tails that we barely have any room to write in, we find the remaining 0.15% out here in the tail, past that. So out here past that cutoff, we find 0.15% of the population. This is something that you might want to put on your note card, and the good news is you can simply pause this and copy this neatly onto your note card. Okay? I would recommend doing that. I think you'll find it helpful. Now, sometimes people land exactly on the deviations, like if the average IQ is 100 and the standard deviation is 15, someone's IQ might be 115. Well, the next cutoff would be 130, but there are people who have IQs between 115 and 130, and we need a way to deal with those people that land in between here. So we have a thing called a z-score. I'm going to come back to this in just a second. A z-score, or standard scores, determine how far, in terms of standard deviations, a given score is from the mean. So it measures, a z-score measures how many standard deviations you are from the mean. The formula for finding z-scores is the value of the piece of data minus the mean divided by the standard deviation. So this is probably a more useful formula right here. Z is equal to the data minus the mean, and notice that sometimes they use mu depending whether we're doing sample or population, divided by the standard deviation. So that's the same as the mean minus mu over sigma. Okay, so we take the value that we're wanting to see how far it is from the mean, subtract the mean, and divide by the standard deviations. That will tell us how many standard deviations that we are from the mean. Okay, let's do a couple of those and that will help. We have a normal distribution with a mean of 100 and a standard deviation of 20. So I'm going to actually draw this. We have a standard deviation. Imagine a perfectly bell-shaped symmetric curve. It says that the average is 100 and the standard deviation is 20. So we'll have 3 cutoffs above this on the normal curve, right, and 3 below this. And each time we go to one of the normal cutoffs here, the regular ones, we go up by 20. So this would be 100 plus 20, 120. This would be plus 20 again, that would be 140. And 160, subtract 20 and we get 80, subtract 20 again, 60, subtract 20 again, 40. Okay, so it wants to know what's the z-score for 140. This is my data item. This is my average. right? And this is my standard deviation, 20. So I'm going to take the mean, the data item 140 to get the z. It will be equal to the data item minus the mean, look up here, which is 100, and divide it by the standard deviation, which they told us was 20. So that's going to give me 40 over 20, which is positive 2. So the number 140 should be 2 standard deviations above the average. So we go to the average, 100, 1 deviation up, 2 deviations up. Sure enough, we find the 140 is 2. So the z-score is 2. It tells us how many deviations, and it's always positive or negative. We have to know the direction. This was positive. Okay, where would 80 be? Let's look at this. It was 1 deviation below. So we should predict that the z-score will be negative 1. Let's go ahead and calculate that. The z is the data item, which is 80, minus the average, which was 100, divided by the standard deviation, which they said was 20. So I get a negative 20 over a 20, which gives me a negative 1. As we predicted, 80 is 1 standard deviation below, therefore the negative, the average. All right, continuing on here, we use 100. How many standard deviations is the 100 from the mean? It's right on the mean, so it should be 0. Okay, let's calculate it. The data value is 100 minus the average is 100. Divide by the standard deviation, which is 20. We'll get 0 over 20, which is 0. And of course, it is 0 deviations from the average. It's right there. Okay, another z. I expect you're getting the hang of it now. We take the data, 115. We subtract the average, 100. And we divide by 20. And that will give us 15 over 20. Okay, and we usually give these as a decimal. 15 divided by 20 would give us a positive 0.75. So this is not 1, it's 3/4 of a deviation above. So if we go 3/4 of a deviation above, we don't get to 120, we get 3/4 of the way, and that makes sense because halfway would be 110, 3/4 would be 115. Okay, this is making sense. And again, we leave these in decimal form. And finally, when z is 75, we take 75 minus 100 and divide by 20. Keep in mind, a good thing to do would be to turn off the lecture and calculate these on your printed out lecture notes, then turn back on the lecture and check them. That way you can see if you're getting them on your own. Negative 25 divided by 20. Will be negative 1.25. So it's 1 1/4 deviations below, and that makes sense because 1 deviation would be 80. 1/4 of 10 is 2.5, right? So that looks perfect. Okay. Or use the symmetry. This looks like it comes from something else. Okay. The deal is that when you do these and they don't land on nice values, if you want to know what percentile you're in and you land exactly at the cutoff right here, let's suppose your IQ is right here at this cutoff, then you could say what percentile you're in. Well, half of the graph is to the left, right? So that's going to be 50% over there, plus 34%. So if you landed here, 50% plus 34%, you could say your IQ was at the 84th percentile. 84% of people have an IQ lower than you. Okay? And what percentage would have an IQ higher than you? 100 minus 84%. 16% would have IQ higher than you, okay? And we did that by simply knowing that this distribution adds up to 100 and using these nice cutoffs. But the problem is What if your IQ landed right in here somewhere, halfway in between or somewhere else? We need to be able to calculate the percentiles for the graph. And so here are the procedures for doing that. To determine the percentile between any two values, we draw a diagram. Oh, this looks like it's the harder section. Okay, I'm going to pause a second and get these in order. I think my pages might be scrambled, and we're going to continue this in the next part. Okay, see you in just a second.